gracias. Muchas gracias a todo el mundo y buenas tardes. Lo siento mucho porque no puedo estar con usted, pero la organización de la familia esta semana es muy complicada y no podía viajar. Y bueno, mi español no es rico, es bueno para el coffee break, pero no por una charla. Entonces, lo siento, pero voy a hablar en inglés para hacer una charla en 15 minutos. Okay? So I switch to English. I hope you see my slides and I hope you see my face. So if you don't, just give me a feedback, because there is a delay between the YouTube okay, you can see it. That's perfect. So what I'm going to show you are the results of the study that we have done, sponsored by ESA, and this study follows up what Alex has just presented. And the idea was to understand what kind of orbital constellations is the best for weather monitoring. And the tool we were using is data assimilation. So this topic actually is old, as Alex mentioned. It has been several years now that myself, with many other people, are going around the world, I would say, to argue that we need some global capabilities from Mars. And in fact, the latest document that we produced is a kind of community paper or white paper. Is dating 1 year almost. So we did this and presented for the Mars atmosphere or Mars atmosphere meteorological observations in Paris last year in June, and then we also presented at COSPAR in Athens and EPSC in Granada in September last year. As you can see from this plot, actually from this map, there are like more than 50 people who joined this effort, and these people are spread all around the world, many in the United States, of course, but if you sum up the numbers in Europe, there are quite a lot as well, together with people in Asia, in United Emirates, and Japan as well. So there are many countries and many scientists in these countries who think it's a good time now for having a global mass weather monitoring constellation from orbit, to do what Alex mentioned, having continuous and simultaneous and global missions for the future exploration. So this is a case of science to do exploration. What is the approach that we used when we came out with this community paper? It was a modular approach. So we were thinking to start with a minimum payload and configuration and then build it up with time. So the idea is that a constellation can be, like platforms can be added to a constellation or can be replaced in time. So the bare minimum we thought it was a good optimal constellation is composed of one polar orbiter and 3 geostationary orbiters, as Alex mentioned. Then you can add more polar orbiters. You have more vertical profiles of quantities at different local times. You add another aerostationary, you add stereo capabilities, and then you can have your shop list going longer. You add a near-infrared spectrometer, UV cameras, sub-millimeter sounder, LiDARs, packages, and you are able to observe surface pressure, aerosols with multi-wavelengths instruments, do wind profile measuring, space weather monitoring, and so on and so forth. But the very key point is to build all these capabilities bit by bit. Okay, so the modular approach was key. Now, that was great, but there was no quantitative assessment linked to these words. So these were still nice words. How do we quantitatively assess the impact of these orbital constellations on the Mars weather monitoring? And this is where ESA came into the. So we actually proposed to ESA to do this experiment. And the purpose of the experiment was to provide a recommendation which is based on quantitative data for the number, for the orbit, and for the locations of the platforms that should create a Mars weather monitoring constellation at Mars. And the methodology that we use is called Observing System Simulation Experiments, or OSSE. It is composed of different parts. A nature run, which is basically a high-resolution simulation from a Mars GCM, from which we extract synthetic data. These synthetic data are injected into another numerical scheme called a data assimilation scheme, which is linked to a Mars global circulation model. And that data assimilation module produces what is called an analysis, which is the best estimate of the atmospheric state based on the combination of model forecast and observations. Once we have the analysis, compare again to the nature run, which we consider as the reality of the truth, the atmospheric truth, and we see whether we are, improving or like getting what nature is doing, or we are far away from nature. To give you a clear example, or like at least a real example. So the blue box is now giving you an idea of variables from a nature run. So nature run is a high resolution numerical model that in this case produces zonal means of dust density scaled opacity, which is basically which is proportional to the dust mixing ratio. You can think of it as a dust mixing ratio. It gives you zonal means at 3 different times of a particular Martian year when we had a global storm, a global dust storm. So you see that at solar longitude 307, there was a lot of dust. From this nature run, we extracted observations, which are observations as if we were looking with a limb-looking thermal infrared radiometer on board a near polar, in this particular example, near polar non-sun synchronous orbiter. And then we injected these observations, these synthetic observations, into Mars global circulation model, which was the LMD model. Then if we follow the green arrow, the results of the analysis are the plots on the right, where you see the same zonal means of dust density scale opacity, which are the result of assimilating this near polar orbiter with this point radiometer observations. And in the middle, you see the difference between the analysis and the nature run, which is giving you, okay? So we are focusing on the peak of the dust storm, peak of the global dust storm. And you see that if we only assimilate observations from a single polar orbiter, we have a big bias. We are not able to reproduce the same distribution of dust. And then we repeated this many configurations and many variables. This gives you an overview of the setup. So we use the Martian year 34 as a real year, which we simulated with a nature run. We selected 3 science cases. One with you see in the upper left plot, so you see a yellow square. So the first case, it was a no dust storm case, and then a global storm case, and then a regional storm case. So we had 3 science cases. We had 9 different configurations. Polar sun synchronous, which is basically Mars reconnaissance orbiter. Then a polar non-sun synchronous, which you will see it's called orbiter A. Then we had 2 configurations which were specifically which were interesting for ESA. I'm not going to talk about these here. Then we had a configuration with a polar orbiter and 1 single aerostationary that you can see on the right, on the top right plot. Configurations with 4 mid-altitude, 5,700 about kilometer altitude platforms, which you see on the bottom right plot. Another configuration with 3 aerostationary satellites. So again, very high altitude, and you see this configuration on the right middle plot. And then we added 1 polar orbiter with this 4 mid-altitude, or 1 polar orbiter and 3 aerostationary. So we tried all these possible configurations, but in all these configurations we had thermal infrared radiometers, which were either point radiometers looking at nadir and limb, or image radiometers looking at nadir of nadir, and providing retrievals of column dust optical depth and dust temperature profiles depending on the type of radiometer. Okay, so that was a setup. I want to spend a bit of time to describe this, because it's important to understand what we did. And I'm going to be quick on the results. There are a lot of results. It's a huge report, very detailed. I'm only giving you 1 hint of what we achieved. These on the left-hand side are the biases for the dust density scaled opacity, okay, for different configurations. And on the right-hand side, you basically have the same thing, but in this case, they are expressed as a root mean squared difference between, 1 single analysis and the nature run at different times. Now, I want you to focus on these plots or these panels, because basically what these are telling you is that if you use 3 single aerostationary satellites, or 4 mid-altitude satellites, or a combination of a polar orbiter and 1 single aerostationary, or 3 aerostationary, or 4 mid-altitude satellites, you really decrease the biases, and the root mean square differences are the lowest among all the configurations. If you only have 1 single polar orbiter, then the biases are quite important. So these for the dust vertical profiles, other variables are behaving differently. Now, if we limit, yes, 1 minute, okay. If we limit the time at the peak of the storm, we can calculate a quantity which is called quality score. So let's not go into the details, but basically what happens is that you can define numbers to give you an idea of what configuration is performing better. And apart the MRO configuration and the single polar orbiter, you see that all the others are performing pretty well. And then we repeated this experience for many other variables. We have a column opacity, temperature, diurnal temperature anomaly, zonal wind anomaly. They all telling you basically 3 things, which are the conclusions. The baseline configuration with a low altitude polar orbiter and a constellation of 3 aerosynchronous or aerostationary orbiters, or 4 mid-altitude orbiters, is performing the best. The threshold configuration, if you really don't have money, is a low altitude polar orbiter with at least 1 single aerosynchronous aerostationary platform. Now, the priority configuration within this decade, in our opinion, should be a constellation of 3 aerosynchronous or aerostationary satellites, or alternatively, 4 mid-altitude satellites, because those are actually performing quite well with respect to all the others. And I thank you so much. Muchas gracias por su atención. Y si te quieres, te puedes contactarme al correo que hay sur la slide. Thank you so much.